So we've looked at exponential functions, and I guess it would be time then to look at the inverses of those. So let's graph the inverse of f if f of x is equal to 2 to the x. Now you might want to hit pause for a second and try it, and then go ahead and see how you did. So if you remember, there's a couple ways to find inverses. One way is graphically. And so if we have the graph of a function, we can graph its inverse by reflecting it over the line y equal x. Now, a function has an inverse function if it's 1 to 1. And that means that it must pass the horizontal line test. And so this function in green does pass the horizontal line test, which means a horizontal line does not hit the function in more than one spot. Therefore, when you reflect it over y equal x, that horizontal line becomes a vertical line, and then our inverse will pass the vertical line test. So if I reflect this graph, I'm going to get that. And so that's the inverse function of an exponential. And we have a name for that. It's called a logarithm. Now, if we were not doing it graphically, or if we were doing it algebraically, well, we take y equal 2 to the x, and we switch all the x's and the y's, and then we solve for y. But herein lies the problem. How do we solve this for y? And so we have this new function called the log function, and for short we just write log, and the base of our exponent is 2, so our log is going to be of base 2 of x. So it's like a function, just like sine or cosine or the square root. Those are all functions. So we're doing the log base 2 of x is equal to y. And so that's our inverse function for the exponential y equal 2 to the x. There's two most often used bases for logarithms. If you just see, let me draw an arrow. If you see a logarithm without a base, then it's assumed that it's base 10. And if you see ln, which stands for the natural logarithm, that's a base e. So we never write log base e, we just write ln for the natural logarithm of x is equal to y. And then log base 10 of x is equal to y. Those are the most often used. Most calculators have buttons for those two, but they don't have a button for every different base. And we'll talk later on about how we can change from, let's say, log base 2 of x to be log base 10 or log base e, the natural log of x, so we could use our calculator. Let's take a little look at these graphs and talk about the domain and range and intercepts and asymptotes. So we're familiar with y equal 2 to the x. The domain, and let's look at these graphs next to each other. So for the blue function, the domain is all real numbers. So, put a little arrow here. So x can be any value. I mean, even though this goes up, it doesn't go straight vertical. It keeps slowly moving out. So x can take on all values for the exponential function. The range, on the other hand, this graph gets closer and closer to the x-axis but never touches it. So the x-axis is actually a horizontal asymptote. And so the range is going to be everything greater than 0. And so our asymptote is y equals 0. The range is 0 to infinity, not including 0. And then the the y-intercept is the point 0, 1. Because if I put in 0 for x, 2 to the 0 power is equal to 1. All right, so that's for our exponential. So what about its inverse, the log function? Well, to get an inverse, we switch x's and y's, so we're going to switch the domain and range. So for the log function, the domain is going to be what the range was for the exponential. So for this purple graph, the domain is going to be everything greater than 0. And then the range for my log graph is going to be the same as the domain for its inverse. So that's going to be all real numbers. And you can see for this purple graph, it goes from negative infinity to positive infinity. this does look like it's leveling out, but it just keeps going up and up and up, just at a very slow rate. So the range is all real numbers. Now it does not have a y-intercept because x can't be less than or equal to 0. So it doesn't cross the y-axis, and the y-axis is actually an asymptote. It's a vertical asymptote. So the exponential function had a horizontal asymptote, and it makes sense then, therefore, that its inverse should have a vertical asymptote. And it does have an x-intercept, and so if the exponential had contained the point 0, 1, its inverse would contain the point, just reverse these, 1, 0, because we switched the x's and the y's. So it's really important to always keep this in mind as we progress through this unit and talk about logs, especially when we start solving equations and realizing that for a log equation, that the input has to be positive. All right, so let's look at some examples. One of the things you should be able to do is convert back and forth between a log equation to an exponential equation and vice versa. So if I have this equation, log base 3 of 81 is equal to 4, got another arrow here, do a blue arrow. Let's write this as an exponential. Well, remember, the base, that's the base, raised to this power should equal that number. So 3 to the 4th power should equal 81. How about the next one? The base is 7, so 7 raised to the 0 power should equal 1. And for this last one, 5 raised to the negative 3rd power should equal 1 over 125. And the nice thing is you can check these, and yes, 3 to the 4th power does equal 81, 7 to the 0 does equal 1, and 5 to the negative 3rd does equal 1 over 5 to the 3rd, which is 1 over 125. So sometimes at first I tell students, well, let's just take one where we don't have any variables, we just have numbers, and try and convert it. And so for example, if somebody said, oh, 3 to the 81st equals 4, obviously that wouldn't make sense. Or saying 4 to the 3rd power equals 81. That's not true either. 4 to the 3rd would be 64. So, and one of the easier ones to do is to use this one. Remember that raising the log base 7 of 1, actually log base anything of 1 is always going to equal 0, because the base to the 0 power will equal 1. All right, let's try the reverse. What if I give you the exponentials? And these are actually the ones that students have more difficulty with converting to a log. So remember, we want to write this as a log. And so what's going to be the base of the log? The base of the log is going to be this, the base of our exponential. And then it's going to be, so the log of that base of this number equals that. So it's the exponent that goes by itself. So you can either write 3 equals log base 4 of 64, or you could say log base 4 of 64 is equal to 3. All right, let's try the next one. Where's our exponential? Right here. The exponent is going to go by itself. So 1 is going to equal the log base this of this. So the log base e, and maybe I'll even write that. So at first, if it helps, write log base e of e equals 1. And then you change that to just writing ln for log base e because it's the natural log. And how about this one? Well, it's going to be log base what? The base of our log will be here. So it's going to be log base a of this equals our exponent, equals b. All right, so like I say, it takes some practice, but you need to be able to convert back and forth either way, especially when we get on to solving equations. All right, let's evaluate some logs now that you know how to write those in either form. What's log base 2 of 1 going to equal? Well, what that means, I'll just put a question mark here for now. That means 2 to what power equals 1? Well, obviously it's going to be 2 to the 0 power, don't think I had an answer plugged in here. I didn't. So 2 to the 0 power equals 1. All right, let's look at the next one. 4 to what power equals 64? Well, 4 times 4 is 16 times 4 is 64, so that's 4 to the 3rd power. How about the next one? We've got 3 to what power equals 1 over 81? Now, it might help to think of 1 over 81 as 1 over 3 to a power. Well, that's 3 to the 4th power. 9 times 9 is 81, so that's 3 squared is 3 squared. And it might help to think of 1 over 3 to the 4th as 3 to the negative 4th. And now we have our answer. So 3 to the negative 4th equals 1 over 81. And then finally, 7 to what power equals negative 49? Well, 7 to the 2nd power is 49. But wait a minute. We can't raise 7 to a power and get a negative number. That's never going to work. So that's no solution. Now remember what the log graph looks like. The log graph looks like this. And the domain of the log is 0 to infinity, not including 0. And so when the input to this function is a negative 49, immediately you should have said, wait a minute, there's a problem there. The domain of log has got to be a positive number. So it's no solution. So like I said, and I mentioned it back then, it's really important to always go back and remember domain and range for exponentials and logs, and keep that in mind as we're trying to evaluate and solve.